In the last part of this lecture, I will talk about unsupervised learning of features. In other words, unsupervised representation learning. Now, we've seen that features are very important. They're actually the essential building blocks of neural networks. And if I want to solve a task very accurately, I know that I really need good features. I mean, I want networks that are able to extract really interesting features from the images. And we've seen in the visualization part of this lecture that neural networks, when trained for a classification task, are able to extract very detailed features. We've seen that some neurons are activated by basically seeing patterns that resemble dog faces. But this required a lot of labeled images. Now, the right question here is, I mean, it would be quite good if we were able to actually create such feature extractors by using small number of images, or even better, by images that are not labeled. And that we have actually quite a bit of them, all around. We can actually go around with a camera and every piece, every frame is an image. So if we're able to learn good representations by these images, by just looking at these images and without any labels, that would be fantastic. And humans do not seem to require lots of labeled images for this task. I mean, I'm going to assume that we have good feature extractions in our brain because we're kind of not very bad in visual tasks. So I think human beings are quite good and in constructing good feature extractors without any labeled information. And it would be really great if we can make the algorithms do that too. And again, I'm going to repeat that there's this bigger question of it would be really great if there were universal features that can be useful for any visual task. The main idea is what's called self-supervised learning with a pretext task. So I have a network here that I will call E, representing encoder. And the idea is I have a pre-training running, meaning that I have lots of unlabeled images, and I have a pretext task. It's kind of a pseudo label that doesn't really require a human being to label an image, but it's a label that I create with some toy task that I give the network for each of these images. And I train the image to train the weights, the parameters of this encoder, such that hoping that actually by training with this pretext task, it will be useful afterwards. The simplest, and afterwards, once I train this encoder, I basically take it, put the weights, and now I can train a network, maybe append it with other additional layers, where we call here a decoder, that goes from the input image to the target task. Okay? And here the dimension increases from the representation, but it doesn't have to be the case. You can actually have the decoder going even smaller, for example, a classification task. And this is called what's called the fine-tuning with limited annotations. Now, the simplest idea is what's called the autoencoding model. So a pretext task is to ask the network to be able to look at an image and regenerate it, reconstruct it. And a way to do it is using autoencoder networks, where I have an encoding path that actually takes the image and converts it to a representation that has lower dimensions than the image. And then I have a decoding path that takes that lower dimension representation and again converts it back to the image. And the entire network is trained to minimize the distance between the image and its reconstruction. Now, the bottleneck here ensures that actually the network is not able to learn an identity map, because you can imagine that a network can learn an identity map. Basically, take the image and try to propagate the image information along the side without changing it. But here, because I have a lower dimensional, what's called the bottleneck, the network cannot memorize the image. It has to learn something about how to reconstruct it. And notice that the minimization here, the cost function, only uses the image and itself. There are no labels associated with it. So the goal is really, you want to be able to reconstruct the image as good as possible. And the features that I learned in this encoding path can then be hopefully translated to other tasks, either directly by taking this encoding and feeding any image through this to get the representations here, and then do, for instance, classification based on these representations, or fine-tuning. So start the optimization from these pre-learned parameters and try to get a little bit better for another task with a small number of labeled examples. So what I would do in the end is I would take this encoding path, for example, put a classification network at the bottom of it, append it with a classification network of some layers, and fine-tune these while training these guys with the labeled examples from scratch. In practice, the auto-encoding model looks very reasonable, but it doesn't really seem to work. The features that it learns ends up not being very useful for another task. So, okay, this idea was okay, but it didn't turn out to be great. So what else can we do? Because reconstructing the image itself is just one pretext task. You can imagine other pseudo tasks. The other options can be, for example, you rotate the image and you ask a network to identify with what angle the image has been rotated. So I take the image of this bird here, I can rotate it with 0, 90, 180, or 270 degrees, and I will ask a network to predict one of these 4 classes. Actually, this ends up being a much better pretext task that when I fine-tune the weights that I learned by this rotation task, the algorithm can really be transferred to a new task rather easily. And the same thing for the inpainting. I can take an image, simply crop a certain area, and ask the network to reproduce this area, the content of this area, by looking at its surrounding. You can imagine in both of these guys, the algorithms, the neural networks, they have to learn some semantic information about the image content to be able to understand that, oh, hold on, this has been rotated by 90 degrees, or, ah, yeah, this part is the dog face, so here I should have the remaining of the dog. So they have to learn some semantic information about the image. And they have been quite successful in the past as well. What I want to talk about is actually another approach, which has been extremely successful in the recent years, which is what's called contrastive learning. And the idea is quite simple. I take an image, and I simply feed it through different random transformations that can be, for example, simply cropping the image in different parts, or simply changing the color of the image, rotating a little bit, scaling a little bit, these random type of transformations. And then I feed it through an encoder. Now, after I feed it through an encoder, I expect this encoder to create representations of that image, or the features at this layer, to have similar information, because in the end, these transformed versions are coming from one original image. So if I actually plug in a shallow network called G1, I should be able to convert these representations to things that are very, very similar. Because again, I mean, they are different images for sure, so they should have some kind of discrepancy between them, but they should also share lots of information because they're different transformed versions of the same image. Compared to these transformed versions, if I actually feed another image to the algorithm, the representations of these guys should be very different. So no matter how much I try, I should not be able to convert the representation here to this guy. So they basically show different contents. And the contrastive learning basically contrasts the transformed versions of the same image with different images, and aims to create a representation such that while transformed versions of the same image should have a similar representation, while these representations would be very dissimilar from representations of other images. By representation, what I mean is really the activations at this layer at the encoder. Now, the contrastive loss, we don't have to go into the details of these equations, but the contrastive loss is actually very simple. I simply say that similar images should have high similarity, and dissimilar images should have high dissimilarity or low similarity. So I basically sample positive pairs, meaning that I know that these images have the same content, and negative pairs, I know that they have dissimilar content. And I make sure that the representations of similar images or positive pairs are as close to each other as possible. Now you can actually use any type of similarity measure here. What works quite well in practice is what's called the cosine similarity, meaning that their angles should be very similar. The angle between those representations should be as small as possible. Now, if I do that, I get impressive results. Now, what I see in this plot is the recognition accuracy on ImageNet. What I show on the x-axis are the number of parameters in a network in millions. So in the top, here you have a supervised algorithm, a supervised network that was trained with all these ImageNet images, and with somehow like 20 million or close to 25 million parameters, the supervised algorithm is able to do really well. But notice that that has a lot of images, that a lot of labels in it. Compared to this, the simple approach of contrastive learning does something that's shown on this red line. So what we see here is, we see that as we increase the number of parameters, we build very, very large networks that contains millions of parameters. And we see that if I actually train a network using this contrastive learning approach, and then fine-tune it for the ImageNet, I get really good accuracies, which at some point, if I train a very, very, very large network, but again, completely in an unsupervised manner, it even can get close to the accuracy of a supervised model, and that's quite impressive. And this actually, you can find the details, further details in the paper that I've shown here that was published, I think, in 2019 or 2020. And with that, I would like to end this lecture. And this representation learning, unsupervised distribution learning are extremely exciting and active research areas. I strongly suggest, if you're interested in computer vision, to definitely go deeper and learn about them more. Thank you very much for your time.